Okay, thank you everyone. We're going to go ahead and get started. This is the Sustainable Phosphorus webinar series. I'm your host, Matt Schultz, and I'm joined by a star-studded cast of presenters today as well. I'll be introducing them in just a moment. The topic of today's webinar is the Vermont Phosphorus Innovation Challenge. I want to go through just some technical details and a bit of introduction to the Alliance before we get started. A couple instructions for the webinar. If you could please, and you all are right now, remain muted with your cameras off and don't try to share your screen with the rest of the group. That would be appreciated. We have, of course, finite bandwidth, and the more people who are online, the more we tax that bandwidth, and also things become a bit confusing when we have a lot of crosstalk on the line. Also, we're going to be, instead of doing questions and answers using the audio, you may be wondering, if I remain muted, how can I ask questions? And the way we do that is by using the chat feature in Zoom. And I'm going to show you just how to do that right now. If you are clicked within your Zoom window, you should see there's a ribbon at the bottom of that window. It might be at the top of the window for you, but it's at the bottom for me. And your features may look a little different than mine as they're presented here, but they'll be similar. You'll see both your mute and stop video are over here. And there's also a little button here that says chat. And if you click that chat, it should open a little dialog box like this one at the bottom right. And you can simply type your message or question at any time during the webinar. So during any of the presentations, I'll be logging these questions. You can type them in this box, and then you can send them. You get to select who you send that chat to, and I would recommend you just send it directly to me. My name's listed as Matthew Schultz. You can also send it to the whole group, but it would be better if you just sent it to me again, because it will cause some distractions during the webinar if you send it off to everyone. So please do, at any time during the webinar, send your questions about any of the presentations, and then at the end of the webinar, we'll come back to those chats. I'll paste them into this presentation that you're looking at now so everyone can see the question and the presenters can answer them. Okay, and one further note, if you're cut off from Zoom at any point, please just go back to the original email with the login information and log in again. It's probably just a quick glitch that you can solve that way. So a bit about the Sustainable Phosphorus Alliance. We're a member organization, and we work within North America as the central forum and advocate for the sustainable use, recovery, and recycling of phosphorus in the food system. We're supported by a group of members, and you can see those listed here on the right side of the screen. If you'd like to be a member and support this work, please do reach out and contact us. We have a website, which is phosphorusalliance.org. Most people misspell phosphorus with an OUS on the end. It's just a US at the end. But you can go search us on Google to find us as well. Some of the work we do, we facilitate networking through events like this one. We have an annual forum, and we have other offerings online as well. We do some technical work through our working groups and provide technical input to other organizations that we work with. We also represent the North American Phosphorus Sustainability community, both at home and abroad. And if you become a member, we offer you a branding opportunity to show that you're a leader in this field. One thing I want to call your attention to is that we have all these videos, including this webinar series and a number of other offerings that we have up on our YouTube channel. And you can just search that on YouTube under Sustainable Phosphorus Alliance. This video will be posted there probably in a day or two. So if you want to go back and listen to it, you can. We have over 14 hours of video footage. So if you have a trans-Pacific flight or something where you need to kill 14 hours of time, you can always watch our videos. And the one event that I want to call your attention to is our big event on April 5th in Washington, DC, and that's called Phosphorus Forum. This year, 2019, it's our third annual one. We have a great program. Two of our keynote speakers are Dr. Bruce Rittman, who is the co-recipient of the Stockholm Water Prize this year. Also, former Deputy Secretary of Agriculture, Dr. Kathleen Merrigan, will be presenting a keynote as well. We have a number of updates on our working groups and other activities, including the launch of our new Phosphorus Sustainability Challenge. So we hope you can come to our website and register for that under our events tab on that page. little bit of on our agenda today. I've gone through the introduction mostly here. We're then going to have a description of the Vermont Phosphorus Innovation Challenge given by Caitlin Hayes from Vermont. And then we're going to have presentations by the various contestants in that challenge. We'll save the Q&A for the end. We have a good amount of time carved out for that. And then we'll close up. I just want to frame the conversation a little bit today by stating that the management of animal waste is really a major phosphorus sustainability issue and nutrient sustainability issue. Animal feeding operations are becoming more intensive and centralized, and more animal waste is being produced within smaller and smaller geographies. And that manure and litter is applied to farmlands. Now that's a great way to recycle nutrients, but when those lands reach their buffering capacity, those nutrients tend to wash away with precipitation and irrigation, and then end up polluting nearby waterways, and in the case of nitrogen, groundwater. Ideally, manure and litter produced in nutrient-saturated watersheds would be exported to nutrient-deficient watersheds, but because those products are mostly water, they're heavy, and they're prohibitively expensive to export very far without drying, and drying itself can be uneconomical. So the U.S. state of Vermont is by no means the only state that is dealing with nutrient overapplication issues. Pollution of lakes such as Lake Champlain and have forced the state to grapple with how to better manage its manure and litter, though. And so one approach they've taken is to foster waste management innovation, which is what inspires the Vermont Phosphorus Innovation Challenge. And the hope is that new technologies will emerge that will do a better job of managing animal waste than what is currently available. So our speakers today include, and I'll let them give their own bios during their talks because we have 6 of them, but first we'll be hearing from Caitlin Hayes. She's the Agricultural Water Quality Specialist from the Vermont Agency of Agriculture, Food and Markets. And then we'll have a set of presentations from contestants, first from Bobby Levine from Digested Organics, then from Jim Jutras and Raju Bhattareddy, and then from Mike Curtis and Eric Roy. And so without further ado, I guess, Caitlin, I can stop sharing my screen and you can share yours and take over.
Great, thank you, Matt. Let me just get my screen up. Hopefully everyone can see that.
I can
yes, great, wonderful. So yeah, my name is Caitlin Hayes. I work with the Vermont Agency of Agriculture as a agricultural water quality specialist. And the Vermont Phosphorus Innovation Challenge is the governor's initiative that began last year. It was launched in April of 2018 to address this phosphorus imbalance that Matt was just describing, where we have this waste that's produced by livestock in the state, and then we still have other fertilizers and feed that are getting imported, therefore creating an imbalance in the state that can lead to excess nutrients getting into our waterways. So once the Vermont Phosphorus Innovation Challenge began, VPIC for short, it was managed by 3 different agencies in the state of Vermont. So the Agency of Agriculture, in which I am a part, the Agency of Natural Resources, and the Agency of Commerce and Community Development. And so there have been parties from these 3 agencies, as well as a slew of folks from various academic, industry, marketing backgrounds that have helped us move this idea forward as a reverse pitch. So we put a pitch out to have innovators and business folks submit ideas that could help Vermont address this imbalance that we have in whatever ways that might make sense. And so in April, we launched the event, and we had over 27 participants show interest and submit business proposals to VPIC. And then we had a smaller number of folks come and present to us in September of last year. And at this point in time, we have 6 participants that are in stage 2 of VPIC that have been allocated a certain amount of funding to do a business case and prototype development for their project, all in the hopes of addressing the phosphorus imbalance and, if possible, creating some kind of return on investment for whatever is produced through the extraction of phosphorus. So these are our participants at this point in time. 3 of these folks will be speaking, so I won't, I'll let them introduce themselves, but I did want to identify that our other 3 participants that are not participating today. So we have Rock Dust Local, which is a company based in Bridport, Vermont, that manufactures, applies, and studies minerals and mineralized biocarbon soil amendments that are deployed in fields to manage SRP and nitrogen losses through broadcast field applications, animal bedding mixtures, and in situ filtration media. We have Green State Biochar, which is based in Barton, Vermont, and they use local renewable organic waste materials that are processed in an innovative machine that's developed in Vermont that produces a sequestered carbon product called biochar. The phosphorus capture system utilizes the biochar that acts as a filter to capture most of the phosphorus that's leaving fields and producing soil amendments and fertilizers that are available for local reuse. Then our third participant that is not participating in the webinar today is AgriLab Technologies based in Enosburg Falls, Vermont. And they use a combination of existing phosphorus recovery technologies, composting and drying equipment, and associated best management practices to demonstrate the technical feasibility of stabilizing and adding value to recovered pea cake and similar materials. Then our other 3 participants will be able to give you their introduction, explain a little bit about their technologies. These are some photos here, and if there are questions about VPIC or the next stages of VPIC, my contact info is here. Folks are welcome to reach out to me. The stage 2 of VPIC will end at the beginning of August of 2019, and from that point in time, there'll be a stage 3, which will embark on full-scale implementation of one or several of these projects. So without further ado, I will let our participants dive into their discussions.
All right. Well, good morning, everybody. Thanks for your time this afternoon and listening to what we have to say for our presentation here about our entry into the Vermont Phosphorus Innovation Challenge. We are based in Farmington Hills, Michigan. We're an advanced filtration solutions company. We particularly have expertise in filtering manure, which notoriously has been very difficult for people to filter because it is so full of fibers and grit and solids. And so we've developed an ultrafiltration system that we think can very successfully manage phosphorus as well as pathogens in manure. So this is a little bit of an overview of our process. We typically start by screw pressing raw or digested dairy or hog manure. That pulls out a fiber that sites can use as bedding for animals, especially on dairies, or to make compost. The pressate, or the liquid manure that comes out of the screw press, goes into our ultrafiltration system. That splits it into 2 streams. One is called the UF permeate, or some people refer to it as tea water. And then the other product is the UF concentrate, which is a high solid slurry that is useful as a fertilizer. So in this project, we're mostly going to be talking about this ultrafiltration step, where we split liquid, raw, or digested manure into this filtrate product and a concentrate product. And as you'll see, the concentrate product is where about 90 to 95% of the phosphorus will remain, whereas the permeate product is a transparent, tea-colored liquid that has no pathogens, no suspended solids, and very, very little phosphorus. Just to mention it, we can take that low solids material that you have permeate to another process, which we call 2-step reverse osmosis. And really this is a combination of forward osmosis and reverse osmosis technologies that allow us to further dewater that to make another concentrate product, which is the RO concentrate shown here. That's rich in ammonia and potassium. And then a clean water product, which can be used for animal drinking water or discharge to waterways. So again, for this project, we're mostly focusing on the first step where we're going to take a raw digested manure, we're going to release fiber in the screw press, UF permeate, and UF concentrate. So we're aiming for roughly 75% of the total manure volume to be a liquid devoid of phosphorus, pathogens, and suspended solids. So our project summary was to assemble and operate a pilot-scale ultrafiltration system at 3 Vermont dairies, and this would allow us to demonstrate the efficacy and cost-effectiveness of our stainless steel tubular system. This is a picture of a small mobile system we've developed for another application, but would be similar to what we'll be bringing to Vermont. And just so everyone knows, this will probably be happening in the late March timeframe, and we'll be having open sort of public opportunities to come see the unit in operation and learn more about what we're doing. The idea behind our model is it's a hub and spoke model where we will identify hubs such as composters where we can bring the phosphorus rich concentrate while putting ultrafiltration systems on small and large farms around that hub. So the idea is to collate the phosphorus-rich material at the hub and have independent processing systems sort of be the spokes. And the idea is that we can essentially concentrate the phosphorus in large volumes of manure into very small volumes of concentrate, cost-effectively transport that to the hub, and either process it for use within the watershed or for export out of the watershed, depending on what makes the most sense. So some of the benefits of doing on-farm ultrafiltration, obviously we're targeting reduced runoff of phosphorus into nearby surface waters. We want to help farmers improve their agronomic practices, because keep in mind, farmers still need the fertilizer components of manure to grow crops for their animals in many cases. But we want to keep that phosphorus in the soil and working for the crops, not running off. Our system also removes E. coli and other pathogens. That's been a big problem in different parts of the country, especially where there's not a lot of topsoil and having well water become contaminated. So we want to manage that. We want to reduce soil compaction by concentrating nutrients in manure. You can then apply nutrients with fewer gallons per acre, so less time spreading and hauling. And then obviously take trucks off the road, which has a tremendous benefit to the community, less wear and tear on the roads, less odor, things like that. For the farmer, the benefits of on-farm ultrafiltration involve reducing their hauling and spreading costs. So again, we're concentrating their nutrient value, making it more cost-effective to apply. Ideally, they can use lower cost methods for UF permeate, so there's no longer any solids in it, so it's easy to use irrigation equipment, drag hoses. Often you can apply more gallons of UF permeate on crops or acres closer to the farm at a higher rate per acre, so that reduces the overall transportation costs. In addition, this concentrate now could potentially be a new revenue source for the farm, as they either sell that concentrate to the hub or other fertilizer manufacturers. And as I'll explain soon, because we don't use any polymers in our process, it can be an organic certified fertilizer product, which would bring more value to the farm. And then we have talked to several farmers about improved agronomic practices leading to higher crop yields, especially through reduced runoff, as well as the ability to apply permeate to crops during the growing season, especially during dry years. So I want to tell you a little bit about one of the installations we already have, just to kind of show you some pictures and tell you a little bit about how the technology works. This is Majestic Crossing Dairy. We installed this system a couple years ago in Sheboygan Falls, Wisconsin. It's sort of a 3-bay system where we have a manure pit and some process tanks in the leftmost bay, screw presses in the center, and then our ultrafiltration and 2-step RO process in the rightmost bay in this picture. And many of you are probably familiar with screw presses. They're very commonplace on farms. So this is just some analysis on the dry material coming out, which shows you that it's about 30% dry matter. It does contain some phosphorus, as well as some other nutrients. Again, it has some value as a compost feedstock, or many dairies fed their cows on that material. This is what the ultrafiltration system looks like. So it's comprised of stainless steel modules that are bolted and welded together. The actual membrane that's doing the filtering is a 3/4 inch internal diameter stainless steel tube with a porous or sintered wall. So it's a very robust platform, very abrasion resistant. It can handle high temperatures, high pressures, extremes in pH. This top picture here on the upper right shows what the UF permeate looks like. That's the tea water coming out the top. So essentially, the liquid manure is pumped into this system. It's recirculated by a recirculation pump, so it's being pumped through these tubes. The permeate is the liquid that actually goes through the wall of the tube. The solids stay inside the tube, and the permeate fills the shell and exits at the top. The concentrate, you can't really see it in this photo, but it exits behind the unit. This is a picture here on the right of what one of those individual tubes look like. And again, what's unique about this is that it's designed to last 10 to 15 years. So we're trying to put in a very robust piece of equipment once and not be replacing parts or filter elements very often at all. There's no moving parts inside it. There's just a pretty run-of-the-mill centrifugal pump. It can be tuned to operate in batches. So if you filled up like a manure pit or a manure tank, you could batch that down. It could also run continuously. It can be mounted horizontally like you just saw in that picture, or vertically if it had to take up less footprint. And then again, we're using no fancy polymers, no chemistry here. This is a chemical-free process that's simply relying on the average pore size in that membrane, which is 0.02 microns, to retain the solids and the pathogens, but let the water and some of the dissolved salts pass through. So just to give you a sense of some of the a recent analysis we took at this site, the liquid manure comes in at about 5.3% dry matter, and it has 10 pounds of P2O5 per 1,000 gallons. The UF permeate comes out at 1.4% total dry matter with 0.2 pounds of P2O5 per 1,000 gallons. So that's about a 98% removal rate on phosphorus. It also, every time we've tested for total coliforms or E. coli, it performs, greater than 99.9% removal, basically to non-detect levels. So it's a very reliable, robust filter that has very consistent performance day to day. This just shows you some additional farms. We've done a couple dozen farms in pilot tests to date, but just to show you this isn't a phenomena unique to that one farm. These are all other farms throughout the country, showing again incoming. The UF feed would be the liquid manure coming in somewhere between 6 and almost 10 pounds of P2O5 per 1,000 gallons, and again, reduction to that level of 0.2 to 0.3 pounds per 1,000 gallons in the permeate. So again, very high removal rates, which would allow a farmer to, I think, use that very successfully for irrigation at high volumes per acre, or continue with our two-step row and reclaim drinking quality water. So we provided, here we have an estimated mass balance for a 500 head farm in Vermont. We're assuming about an 80% permeate recovery. So that means if 100 gallons of liquid manure go to our filter, 80 gallons come out as UF permeate and 20 gallons come out as concentrate. So this is, the modeled, 15,000 gallons per day of manure become 12,000 gallons a day of permeate and 3,000 of concentrate. And here I've shown the concentration of P2O5 in pounds per 1,000 gallons and percent. And then to the right here showing the pounds per year. So that farm has almost 50,000 pounds per year of phosphorus in their manure. We are able to concentrate that, instead of it being in about 5.5 million gallons of manure at the end of the year, now it's in just 1 million gallons of manure. And that's the high solid slurry that we can either help that farmer use more precisely and at fields where it's more cost effective, or we can transport that to the hub where we can help make a high phosphorus compost product, maybe other fertilizer products. In certain places they're talking about making sort of community lagoons where you could store high solids concentrate like that for other crop farmers to take instead of them going out and purchasing synthetic phosphorus fertilizers. So lots of opportunity to, once you've done this concentration, to then achieve the watershed and farmer benefits. Our systems are all highly automated. As you can see, we're relatively simple with just a few pumps in an enclosed system. So there's very little for operators to do. We have online dashboards where the owners can log in and see how much water has been made or how it's filtering today. So a lot of data being collected, very automated, very low headache system for the farmer. I'll leave you with that. If anybody has any questions, we'd be happy to answer it. And looking forward to being on a Vermont farm soon with our unit, and we'll be sending out, probably through Caitlin and some other local groups in Vermont, we'll be sending out invitations to have people come in and see our demo and process.
Great, thanks so much, Bobby. That was a great presentation and apparently inspired a lot of questions. So I think I'm going to break with tradition here, and we're going to do the questions immediately after the presentations. So what I'm going to do, if you could stop sharing your screen, I think you have.
Sure.
Yeah.
Yep.
I'll go ahead and share mine, and then people can see the questions that have come up. I'll just post them in this box here. So the first question we got is regarding the ultrafiltration, whether you think this would work with domestic sewage.
So we have processed domestic sewage and septage, and it absolutely works well. I think it depends on the, sort of what the goal is, but people are already using ultrafiltration in what's called a membrane bioreactor, where you have a sort of a domestic sewage or a treatment plant with activated sludge process, and you then run that material through the ultrafilter to release a clean effluent, and you recycle the biomass back. So that's something that we are, our system is certainly able to handle.
Great. Next question that came in is, what is the cost per pound of phosphorus for step 1? For step 2, and for the dairy, do you have the added cost in terms of per animal unit? And maybe you could remind us what step 1 and step 2 are.
Yeah, so for step 1, where we're doing a screw press and an ultrafilter, typically we can achieve that 80-20 split of filtrate and concentrate for somewhere between 1/2 and 1 cent per gallon of liquid manure. So on a per pound of P basis, again, depending on how you're doing your accounting for capital costs and operating costs, it's significantly less than let's say $5 a pound, and probably quite a bit less than that, depending on what you include in that analysis. And then the 2-step RO, again, typically that's on the order of 1/2 to 1 cent per gallon of the UF permeate going in, and then that becomes, again, another about 70% of that becomes water and 30% another fertilizer product. So on the top of my head, I don't have per animal unit cost, but I'd be happy to contact that person and provide some more information about that.
Yeah, and that person knows how to get a hold of me, so please do send an email and I can connect you with Bobby. Also, what is the experience with blinding, which I understand is clogging of the UV filter?
Yeah, so the UF filter is self-cleaning in the sense that those tubes are basically being scoured clean as it's being filtered. So we're maintaining a sufficient velocity in that tube to keep it clean. So what does eventually happen is some scale will build up over time, just like it builds up in any hot water pipe in your house maybe, or especially on a farm. So the system does go through an automated cleaning process where it'll shut down for about an hour. It'll fill with water to rinse out the manure. It'll fill with like a high pH and then a low pH chemical to dissolve some of that built up material, and then it'll turn back on automatically. So it is a clean in place cycle that occurs about once a week, depending on the site.
Okay, great. 2 more here we're going to do. What is the cost per gallon of the UF treatment, approximately?
Yes, that's what I was saying. Depending on the application, we're usually in that ballpark of about 1/2 to 1 cent per gallon of material being sent to the filter.
Yeah, sorry about that. And then the last question being this one. What are the UF farm system power requirements for?
So, it's wise to point that out. So our largest operating cost is certainly electricity. You'll be well served to have 3-phase power, and obviously the lowest electrical rate you can get will reduce your operating costs. Or for farms that already have digesters with gensets, to me, I think it's a perfect marriage of technologies, because you can use the energy and manure to then run a filter to sustainably process that manure. So I think certainly 3-phase 480 volt power is import, we are renting pumps, and that's the largest operating cost.
Okay, sorry, Bobby, this really is the last one, and then we'll get on to Jim and Raju's presentation, which the last question is what happens with the CIP from the cleaning?
Yeah, so after cleaning, you're gonna have, so what we'd call like a spent cleaning fluid that would typically just go into the lagoon of the farm and get spread along with that manure. And so typically these are very common, just, like a caustic soda kind of material that would, the rate we're using it at of, maybe a gallon would get diluted into, 50,000 gallons of manure. It would be undetectable later in time. It would just look like a little bit of extra salt in your lagoon. So it would all just sort of get dissolved.
Great. So thanks so much for that. And I'll stop sharing now. And Jim and Raju, if you want to begin your presentation, we can move over to that now. Thanks so much, Bobby. Jim?
Okay, I believe I'm sharing here, okay?
Yep, I see you.
Okay, very good. I'm going to introduce myself first, and Raju will be following shortly. I'm James Jutras. I'm the Water Quality Superintendent in the Village of Essex Junction. Our work here involves both wastewater and stormwater. We're a small municipal separate storm source system, or MS4, as well as a large wastewater facility by Vermont standards, but a very small one by national standards. I like to use the comparison that the City of Boston's Mass Water Resources facility on Deer Island has a pilot facility that's approximately the size of our current operation here. So when we're looking at compliance with permits, costs are real. Phosphorus is a big challenge with the Lake Champlain TMDL for phosphorus, which also includes stormwater. So we want to and need to find something that's cost effective, that fits the Vermont scale, and also has some potential benefit in other sectors. Our challenge here is high, like it is in most areas that have nutrient limitations. The motivating factor for a lot of what we have done is the big overriding one from the village side of things is that during the EPA TMDL public hearings, one message resonated consistently and powerfully clear by EPA, and that was if there is failure to meet the objectives of the TMDL, their only recourse was to go back to MS4 and NPDES wastewater facility discharges. So we've been doing phosphorus removal to 0.8 since the 1980s, and now we're treating to 0.2 under the TMDL. And there's some litigation going on in the state that may require a lower level if the litigation is successful. So again, we've got the TMDL as an overarching incentive for us to do this work, P reduction across all sectors. We had this concept brainstormed about a year ago, and then we caught wind of the reverse pitch that was being done by VPIC. So we submitted under that program, and fortunately we were successful. This is a partnership that we're doing that involves the University of Vermont, the Village of Essex Junction, Efficiency Vermont, which is an electrical efficiency utility, and the Chittenden Solid Waste District, which is a district that manages the sludge or biosolids from facilities in their service area. There are some good potential business and economic development opportunities here, both directly with the project as well as the ability to treat more wastewater without coming up against our limits of our operational permit. And that's especially important because we recently went through an upgrade here, a maintenance upgrade of this facility. And all we did was go through the facility to meet the permit at the time. And that was a $15 million project for a service area of about 30,000 people. So to do any additional phosphorus reduction beyond what we can do right now would have a significant cost with diminishing returns as we continue to invest in this. We are also saddled with a 40% reduction within the stormwater system to comply with this TMDL. So in looking at this, we needed something that was cost competitive. It had to have broad application for the various size wastewater facilities in this area, and it had to be scalable and easy to operate. And what we came up with is something that uses conventional descaling equipment to help with particle alignment. And then Raju Badareddy's work with ultrafiltration to do the polishing. And overall, we're at the beginning of the system. The descaling technology is going to be installed this Thursday, with the pilot work to be done in the laboratory immediately following as the school semester is in. And then as soon as we get out of this bitter cold snap that we're having and get some preliminary information out of the lab, we'll look at the scale up based on those findings to do a pilot using centrate or dewatered digested supernate from our anaerobic digester, and do the scale up for the bench work that Raju's doing. So with that, I'd like to hand off to Raju Badareddy right now. If you could introduce yourself, Raju.
Yeah. Oh, you have to exit screen sharing, I guess. Okay. I'm Raju Badareddy at Civil and Environmental Engineering Department at the University of Vermont. My major research interests are in developing novel membrane materials or self-cleaning membrane materials for water and wastewater treatment and resource recovery. So for this phosphorus project, Jim and I have talked about how to recover the soluble phosphorus from these waste streams at the wastewater treatment facility. So after long discussions, we have come to a decision to take two different approaches. One is using this particle descaling technology to transform soluble phosphorus into particulate phosphorus. And this technology is commercially successful, and it has been shown to transform inorganic compound or soluble inorganic species into particulate species. So along those lines, we were interested to explore to see if this technology can transform soluble phosphorus into particulate phosphorus. So there is no data available yet, but what we are, based on this project, we are going to treat the waste side streams at the wastewater treatment facility, and then we kind of recover this particulate phosphorus, and then we will using dead-end filtration. The main focus of this dead-end filtration is to basically study the composition and the quality of the recovered phosphorus, which could be struvite or vivianite. And also we will be looking at the particle size distributions and so on. So depending on these particle size distributions of these recovered phosphorus, we will either use microfiltration or ultrafiltration or nanofiltration membranes to recover this phosphorus. So once this particular work will guide us to choose the right type of membrane, and then we will couple this particle descaling technology with a cross-flow membrane system, which we call it as an electric membrane filtration system. This is the membrane system that is being developed and researched in my laboratory at the University of Vermont. Basically what this filtration system does is, we will pass the waste stream that's treated with particle descaling technology over this membrane. And then using a weak or low electrical fields, we will try to keep these particles in suspension while filtering the water. So it does, there are three benefits associated with this method. One is we can keep the phosphorus product in suspension while filtering the water from the waste stream. So the concentrate or the retentate that comes out of this membrane system will be highly concentrated P product or struvite or vivianite. And the filtered water will be low in phosphorus, nearly most of the phosphorus removed, which is kind of captured in the particulate form in the concentrate. And having these weak electrical fields across the membrane keeps the membrane pores from clogging. So this is a kind of a cleaning technique that we incorporate into the system. This will minimize the membrane cleaning process for a long period of time and keeps the membrane functional also for a long period of time. This is more of an anti-fouling technique that we are incorporating into this membrane system. So again, we will be looking at the quality of the p-product that we recover using the system, and how much we can recover, and so on. All this is a part of the research in this project. So we all know that most of this phosphorus, the soluble phosphorus, easily migrates in the environment, and with our proposed process, we anticipate to capture most of the soluble phosphorus in the particulate form, so there won't be any dissolved or soluble phosphorus left in the water. And this will also reduce the burden to treat the waste streams, or retreat the waste streams, or recycle the waste streams for further treatment. And another advantage is there will be less soluble phosphorus in the biosolids, which is also a valuable byproduct from these waste water treatment facilities. And also, as you all know, most of this soluble phosphorus, if you were to transport to a different location, the majority of it is water, which is, and the mass of water to transport is very, very expensive. So by removing the soluble phosphorus, we will also be saving a lot of money in terms of transportation costs and so on. And one of the big, the major drinking water source for us in Vermont is Lake Champlain. And we can also mitigate the phosphorus runoff into this Lake Champlain and protect our waters. The market opportunities for phosphorus are emerging and also developing locally as well as nationally. And in addition to recovering phosphorus in the particulate form, another product, a valuable byproduct from this process will be biosolids, which will have low soluble phosphorus, and also the treatment with the particle descaling technology will also mitigate the presence of pathogens and so on. So there is a potential for these biosolids to be used as a fertilizer, and also depending on whether there are pathogens or not, it can, if there are no pathogens, then we can apply these biosolids as a Class A fertilizer. If any pathogens left, then we will further treat this and apply as a Class A fertilizer. Again, this is all a part of the research, which we are going to explore in the next few months. Like coming to the operation and maintenance issues with our system, at the moment, we don't foresee any operational issues, which I'm going to get into a little later. But varying waste streams is a daily part of the operation at wastewater treatment facilities. So these systems at the facility, there are various options that are available. We can install the system and then treat a variety of waste streams. For example, liquid digestate from the anaerobic reactor, or centrate from the centrifuge, manure pit liquid, and so on. All these streams can be treated with the particle descaling technology and the membrane filtration. And also, if needed, there is an option to add coagulants and flocculants. But again, the research that comes out of this work in the next few months will inform what modifications we need to adapt to recover phosphorus and so on. And we are aware of these, uncertainties, like varying performance depending on the feed water conditions and so on. We will keep these into considerations while performing this work. Yes, our technology it will be able to treat multiple waste streams. It is a very simple system, flexible and also cost-effective. If needed, again, we can easily incorporate coagulant and flocculant units, and we can couple these systems to the existing system, and then we can evaluate how much phosphorus we can recover and so on. And the major part of this work is also evaluating this anti-fouling membrane system using small amount of electrical fields. And these electrical fields, or the electricity, will come from so we can hook it up to a solar panel, and the energy provided by that solar panel will be sufficient to keep this membrane clean for a long period of time. So what are the implications of our approach? And the objective, the TMDL objective in Vermont is about 0.2 milligrams per liter, And we all know the advantages of meeting this TMDL or beyond TMDL. With our proposed process, it is possible to reduce the soluble P in our waste streams, and these also sludge production will be reduced. And using this low amount of electrical fields, we can keep the membrane clean while recovering highly concentrated, highly pure phosphorus from the waste streams. And pathogen control, all these are various possibilities that can come out of this project. So in essence, our technique or our system is very scalable. It can be easily installed on various pipelines and investigate various side streams and various feed streams and evaluate on how much P can be recovered and so on. And also the other major thing that we are going to look into is this novel membrane system, which is designed to be anti-fouling while filtering the membrane, filtering the water and recovering the phosphorus and so on. This is a very simple application aimed at Vermont-sized farms and wastewater treatment facilities in Vermont. And finally, we would like to thank our funding agency, Vermont Agency of Natural Resources, Village of Essex Junction, and Vermont Energy Investment Corporation for supporting this work. And also we thank our collaborators, James Morris and Josh Taylor, for valuable insights and feedback. Thank you.
Yeah, thanks so much, both Jim and Raju, for that presentation. It was great. We're gonna, and one of the nice things about it was you did treat the wastewater and stormwater pieces of this puzzle, which I failed to mention in the setup to this piece, but they're certainly integral to solving the phosphorus pollution problem. We do have a few questions that I want to go to before we go off to our last presentation. So I'll go ahead and share those. Hopefully you guys can see this. So the first question is, how does side stream treatment translate into reduced P in final effluent?
Raju, if I could take that. We identified at the facility in meeting the 0.2 discharge that we're currently performing to, that 40% of our soluble phosphorus load was in recycle from the digested sludge. So by interrupting that 40% recycle back into the facility, we would be able to increase the P reduction capacity within the plant and not have to add conventional processes. The conventional processes have a significant cost, and they also typically generate significant amounts of sludge that require treatment again. So it's like a constant cycle to maintain this, and the initial thought was to find a way to interrupt that cycle, and that's how we ended up where we are today. Would you like to add anything, Raju?
No, that's it.
Okay, great. Jim, this was another one that was directed at you. You mentioned stormwater P reductions to meet TMDLs. How do you envision using this recovery process to dilute non-point sources such as stormwater and farm runoff? And you did address that a little bit, Raju, but maybe you could go more into it, Jim.
Well, I believe, and if this product works the way we envision it, we'll be reducing it significantly at the facility, which is also in the same permit sector, meaning lake segment within the Lake Champlain Basin. And by meeting the 0.2, we're all, besides finding that 40% increase in recycle, we're also finding our land application program, which involves a farm partner right here near the facility, has higher numbers of soluble P, which we would expect. And because of that, we are now applying the sludge of the treated biosolids with total soluble P as a limiting factor. Because of that, our application rates have gone down in order for the farm to comply with their agricultural practices. So number one, we're using this process to reduce the amount of P that we're recycling back into the environment as biosolids and getting it out of the Lake Champlain Basin, or at least in areas, out of the areas where we have a higher P number. The the farm side of things, we're going to pilot some manure as part of this, and it may be heavy manure, it may just be the cleaner liquid off the top. We're not quite sure yet, but that's where Raju's work comes in. Stormwater as well, there are some higher concentration areas where this kind of an application may have some efficacy as opposed to other conventional areas. The TMDL is complex. It involves many, many different lake segments, and the research that's being done, especially on the lab scale, will give us an indication on how much applicability this will have from small and large phosphorus concentrations.
Okay, great. We've got another one here. Maybe Raju, you can address this one. Will research results be published outside of the challenge, for example, in journals, conferences, additional webinars?
Yes. This is one component. This project is one component of my research, but we are developing these membrane systems to recover nitrogen and phosphorus, and also evaluate the pathogen reduction and so on in my laboratory. So the work that we are going to produce using this VIP funding, we are going to, of course, publish it, in journals and conferences and so on. That's the outcome. There are grad students working on this project. Eventually, they will publish this work.
Great, thank you. And then Caitlin, you thought you were off the hook, but we got one for you. This will be the last question we take on this topic. Do you or others have a handle on the P nutrient loading on an annual basis into Lake Champlain from all of its sub-watersheds? I believe these are reported.
Yeah, I think that we do have. I mean, it is very hard to know specifically how much dissolved phosphorus is going into Lake Champlain from all the sub-watersheds. I can look into getting some more information on that and send it back to you, Matt, and then we can share it with all the webinar participants.
Okay, great.
If I could add, Matthew,
yep.
This is part of the Lake Champlain TMDL by sectors, and it is available. I'll work with Caitlin if she needs some assistance to get that out. I will point out that wastewater facilities, their pollutant load is less than 4% of the problem, yet we're one of the two that are identified as the only recourse for EPA. So that's why this is extremely important to us and why we appreciate the opportunity to work on this with the VPIC and with Caitlin.
Yeah, great. Thank you, Jim. Okay, so our last presentation can start. So I'll stop sharing, and Mike and Eric, you can queue up your presentation. And again, if you all have questions, please do forward those to me via the chat feature. Some of you have been doing that. There are plenty of you on the line, and we'd love to hear from all of you. So please.
There we go. So this is Mike Curtis, and I'm sitting here in the middle of ice. Had the extreme pleasure to come home last night off of an airplane, which was 4 hours late, and chipped 0.2 of an inch of ice off my car. Took me an hour. And I froze. So anyway, this is, everyone's getting this because I'm a bit of a technical dinosaur.
Yeah, we're seeing it, Mike.
Good stuff. Okay. So I am a project developer for a group called Quantum Biopower in mid-state Connecticut. I work with a variety of firms and I have a lot of work going on with DVO, which is perhaps the largest agriculture-based digester company in the U.S. We're teaming with the University of Vermont, and we've got a very good relationship in soils development and soils market development with a company called Synergy, which makes a product called Magic Dirt. It is out in 2,700 Walmart stores as we speak. And I'm here with Eric Roy today, who, if you have questions on the biology of what we're driving at, he is by far the best person to answer those questions. So here we go. So bear with me. Okay, there we go. Okay, so very brief process overview. I mean, we are working with DVO digesters in the state of Vermont and other digesters potentially. There are 13 agricultural dairy-based digesters in the state. And digestion, for those of you who don't have it, is basically 22 or 23 days of exposing manure to about 102 degrees Fahrenheit and a lot of microbiology in the absence of oxygen. And as our first speaker ably detailed. We have a two-step mechanical process. The first one is identical with theirs, which is we have a mechanical screw press in every situation, which produces a 25 to 35% solid, 25 to 30% solid, which is commonly used as bedding in its recycled form. It also, in a variety of situations nationwide, is the basis of a commercial product called Magic Dirt. And there's a whole, the market for that material is evolving, but it's a very robust material that's available pretty much nationwide, mostly in Walmarts at this point. Secondary solids, as detailed prior, are contained in what I like, you can call what you will, I like to call it the juice that comes out the side of the press, and it contains most of the phosphorus. Estimates 80 to 90%. This phosphorus is in general borne on fine solids, and removal and management of these solids after they come out the side of the press is really the key to phosphorus control. Okay, our technology, this is not pilot mode, but there are 10 systems in place nationally and one in Vermont at this point, is a modified DAF, dissolved air flotation system. For those of you unfamiliar with the technology, it's like an aquarium bubbler with minor use of a food-grade polymer, which floats solids to the top of this system where they are skimmed and subsequently pressed into a fertilizer product. These are, in every case, run by farm staff nationwide, and the implementation of this DAF technology has been shown to reduce manure phosphorus levels from 85 to as much as 92, but 90% from the digestive solids influent to effluent mass balance. As detailed, most all, near all of the phosphorus is contained in the pressate off the screw press, and removal of this solid-borne phosphorus can remove the 90% plus of the phosphorus in the pressate. Okay, these systems nationwide are a latch on to a digester. It's an additional unit process. There are no modifications to an existing digester in place. It simply takes the materials, the digestate on the far end, presses them, and then treats them further with this flotation technology. Its power use ranges from 100 watts to a kilowatt, and its chemical use is, as detailed, a food-grade polymer. The all-natural, yes, it is a food-grade polymer. It is not at this point deemed quote-unquote organic due to the polymer use in this system. These are 12 of these systems that have DVO digesters in place, and the engine size associated with these digesters is shown, the year built is shown, and there's a lot of cows and manure in these things. The first one, Blue Spruce Farm, actually has 2 digesters in place, and these are statewide, throughout, mostly in Addison and Franklin County, up in the northwest and the central west part of the state of Vermont. Right, and we believe, or we hope, that given the effectiveness of phosphorus recovery, and we do have a potential for very little capital cost, we believe that farms will participate. If that occurs, we are looking at the potential capture of as much as 650,000 pounds of phosphorus annually, which is equivalent to about 1.5 million pounds of phosphonate P2O5 phosphorus fertilizer. And that's contained in a much larger mass of solids, which is removed with this technology. As you can see, you can just do the math, it's approximately 1.5% phosphorus in the solids that are taken off the dissolved air flotation system. Right? The group that is developing this into a product that we are working with is a group called Synergy. They have taken the primary solids from DVO digesters and turned it into a very successful retail project called Magic Dirt. We are looking to create a Vermont product, a new line of plant foods, right? It's a fertilizer product. And in order to get to how it performs, we are working with UVM in the first grow testing of this material. The products currently, the primary solids, currently go to 5 regional distribution centers, each serving about 80 to 120 stores, and they are distributed nationwide throughout the Walmart chain. Right. Magic Dirt products from Vermont digesters, they're currently being collected from 3 digesters in the state, have been shipped to distribution centers in Pennsylvania. And as well, best we know, as it relates to this secondary solid captured off the dissolved air flotation device, there's no competition for this product. Our experience to date, looking at the results across 10 different systems, 10 different dissolved air flotation systems installed in about 6 states, is a remarkable chemical consistency state to state. Right. And there's no reason to believe that in Vermont, in-state application will make that differ at all. Right. We are taking this material, which looks like so, and our average data, based upon a number of samples, probably more than 3 dozen samples at this point, shows this phosphorus recovery cake, this PR cake, to have 1.5% phosphonate or phosphorus, approximately 3% nitrogen, and about 1.8, 1.7% potassium. It's a fertilizer, and we are testing it at UVM to that end. All right. So our schedule will break this into supply side and product side. This project gets going. We have a series of group meetings and farm meetings which are set up. We'll be working with the Agency of Agriculture, Food and Market, and we are also, in a parallel front, doing grow testing using a formulation brand development that's being developed at UVM with Eric Roy in collaboration with the Magic Dirt people. All right. We will be distributing this over some period of time to retailers, and we've had a number of questions, as working with Vermont on who has what role, and we're rolling this out, and it's a very aggressive schedule, but we're committed to doing it. In the fall, we see installations, sales, commissioning. We see this material. We will be done with the grow testing in the spring semester up at UVM. We have the ability for possible further testing. We will be developing a final formulation, and we have material pickup, bagging, warehousing, delivery, and sales. Those functions, those retail functions, commercial functions, are already in place with the Magic Dirt people. We don't need to reinvent the process with this group. They're already picking up materials in Vermont. They're already taking them to a certain place to be processed, and they are already placing these primary solids in bags and bringing them to a variety of distribution centers. All right. In the fall of 2018, Blue Spruce Farms in Bridport, Vermont, installed a dissolved air flotation system. It's in place, it's commissioned, it's working very well. They've achieved 90% phosphorus reduction from their digestate, and they are producing a cake that allows them to apply what I'll use precision fertilization, and we are using that as the basis of grow testing, which will commence early next month. In 2018, Magic Dirt was working with 3 different farms in state and collecting primary solids, and they've been contacted by 2 others, and that'll be an expanding network of farms, hopefully, that are working into that system. Right. In our 1-year horizon, it's actually spring 2019, we'll be grow testing at UVM. We'll be developing, I'll call it the menu, looking at the assessment of grow effectiveness, and what's done to develop that. In February 2019, there is a very large meeting that I'm not attending with Synergy, where they will be presenting next year's suite of materials to various retail chains. And based upon that, We see this playing out in 2019 and 2020, where we are going to start producing materials late this year, 2019, for placement on shelves in 2020. Right? We see shipping commencing late this year with luck. And we see, as I said, next year, this time, 12, 13 months away, we see the first test market for this material to be in bags on stores at large box retail locations. This all translates back into a cost, which is a value which is developed, for these secondary solids, which we see as being very high. And we are pursuing that in business planning and the final touches of this, the final phases of this project, to bring as much money back to the farms as is possible. Right? And with that, I conclude and can take questions.
Great, thanks so much. Mike, if you could go ahead and just unshare your screen, that I can post the questions up here. It's really the same as when you shared. Yep. I'll go ahead and post those up. So the first question for you is probably going to be a little tough. What is the carbon footprint of transporting magic dirt into Vermont from out of state via Walmart, et cetera? And maybe if that's too tough, maybe another question would be, is there any plan to locally source this in Vermont so that, for example, Magic Dirt would have a facility in Vermont that service stores, Walmart stores in Vermont?
That's a very good question. I don't have a really good answer on the carbon footprint. It is believed to be, there is more. It is sold primarily as a peat replacement, and in comparison to peat, it is very positive in its effect on carbon footprint. It reduces it markedly. The first trial, we do have a commitment. The first trial of this product is projected to be in the Northeast. The first retail run, as it were, is projected to be at the Northeast. So the answer to your second question is yes, we do have a plan to keep it as local as possible.
Great, thank you. The second question, put up here, is how much polymer is used? Where does the polymer go after DAF, and what are the environmental impacts of it?
It is a food-based polymer based upon potato starch, and it is used in the 1 to 3 milligram per liter range. The polymer, where does it go after the DAF process? It sticks with the solids is the answer to the question. It really is tough to pull out, to measure a polymer after it is solid borne. What environmental impacts? It is a highly biodegradable material, and it will degrade in aerobic processes on soil as it is applied. So the environmental impacts are minimal. What the polymer does do to us is keeps us from getting, at this moment, organic certification, which is something we would work on and strive towards achieving.
Okay, thank you. There was a question about what you meant by potential for no capital costs.
It's a very good question. If the value of the solids is projected as high as some entities have indicated, there is an opportunity, not a guarantee, for what I'll call other people's money, for investors to come in and develop these solids reclaim systems at little or no capital cost to the farm entity, and have the farm participate in the financial outcome of the installation. But the capitalization could, and I'll put little quotes around that, could be done by others than the farm itself.
Okay, that sort of leads to another question. I'm kind of going out a little out of order here, but how will the farmers benefit from the sale of biochar in bags at Walmart and dollars per pound to the farmer? What would those be?
The farmer would sell, or the group that put this system in, if it's a collaboration with a farm and an investor, would sell this material to the Synergy folks on X dollars per ton.
Got it. Do you have any notion of what the...
I've seen numbers that range anywhere from 20 to 80
dollars per ton?
Ton, yes.
Yeah.
This is Eric Roy. I just wanted to add, just to make sure there's no confusion, this is not a biochar product that we're talking about here. This is a plant food derived from the digestate. So I've seen biochar pop up a few times. Just wanted to clarify.
Yeah, thanks for that clarification, Eric. Another question that comes up, Mike, can you make claims to the secondary and micronutrient content for greater marketing value compared to NPK only?
I don't know what's implied as secondary content, but the micronutrient content will be consistent with the food that comes in. And, you know, I can't make claims, but I can infer that you know, we've measured NPK, but you know, as it relates to micronutrients in the feed that's coming in to a farm, this will be reflected in the solids that are produced on the far end. I won't want to claim a mass balance, and what goes out is dissolved versus not. I don't know the answer to that, but certainly most of the material in the micronutrient mode will remain on the solids after digestion and solid separation.
Yeah, I think for secondary nutrients, he's talking about calcium, iron, sulfur.
We've got data on those. If someone wants to get to me with a specific question, I can certainly, you know, I can get what data is available.
Okay, and I would just
Mike,
ask,
just to jump in, this is Eric Roy again. We will be doing some detailed characterization of the material we're sourcing from blue spruce as part of the development of the plant food product.
Great, thank you, Eric. Another question here. Thanks for all these great questions, everyone. Does the DAF technology work equally well on raw and digested precipitate?
That's a subject of the next 4 months. It's an excellent question.
Yeah, got it. Let's see, it looks like we have another one here. I'll put it up so everyone can read it. Does the technology only work on farms that have a digester?
It's pretty similar to the previous question, and again, it's something that's going to be investigated.
Yeah, got it.
Yep.
Okay, great. So I think that wraps it up as far as questions go. If people have additional questions they want to address to the panelists, they can go ahead and email me directly and I can put them in touch. I want to thank everyone who prepared these presentations, and especially to Caitlin for helping to organize all the presenters. I think it's been a great discussion, and I really appreciate all the questions that have come in. I would further add that I hope that you all can make it out to our Phosphorus Forum on April 5th in DC, and you can register for that on our website online. We will be getting into our work of our manure and biosolids and manure task force that looks at a lot of the regulations around spreading manure and biosolids on farm fields at the state level, and also we'll be unrolling a tool that will help people look at this problem more holistically. So I hope you can all come out to that. Thanks again to everyone. We'll close out there, and I hope you all have a great day.